Today we will talk about the expectation and variance of random variables. We begin with the basic setup. Let S be the sample space and X, a function from S to R, be a random variable, and script X be the set of values of X. Recall that capital F sub X is the cumulative distribution function called the CDF of X, and P sub X or F sub X is going to be the probability mass function or the probability density function, typically denoted as PMF or PDF of X. We broadly classify the random variable X as discrete if the CDF is a step function, and we say that X is continuous if the CDF f sub X is a continuous function. In the case of the discrete random variable, the set of values is going to be a discrete subset of R. In the case of continuous random variables, it's going to be a union of intervals in R. The cumulative distribution function is calculated as the sum of p sub xy, and in the case of continuous random variables, it is calculated as the integral from minus infinity to x. Things to note about here is that when we are working with discrete random variables, calculations would involve discrete math and combinatorics. On the other hand, when we are working with continuous random variables, we will work with concepts from calculus like continuity, differentiation, and integration. Note that the CDF is the probability that the random variable takes values less than equal to x. This is true both in the discrete and continuous case. Using this formula, we can calculate the probability that the random variable lies between values a and b as the CDF evaluated at b minus the CDF evaluated at a minus, where a minus is the largest value of x, strictly less than a. When working with continuous random variables, the probability that the random variable x lies between a and b would be calculated as the integral from a to b of the PDF f sub x of x. This is going to be equal to the CDF evaluated at b minus the CDF evaluated at a. We note two important facts. If the random variable x is discrete, then for any value c of the random variable, the probability of x equals c would exactly be the PMF evaluated at c. If the random variable x is continuous and c is any value of the random variable, then the probability that the random variable x takes the value c is going to be equal to 0. Next, we will talk about the expected values of random variables. This is the average or the mean value of the random variable x, typically denoted as capital E of x or mu sub x. Of course, there are two cases. If x is discrete, the expected value is going to be the sum over all values of x, and it's going to be x times p sub x of x. On the other hand, if x was continuous, we would be looking at the integral from minus infinity to infinity of x times the PDF of the random variable x. Now, if h of x is a function of x, then we can talk about the expected value of h of x. This is going to be the sum x belongs to x of h of x times either the PDF or the PMF, depending on whether we are in the discrete or continuous case. Note that the definition of the expected value makes sense as long as either the sum x times px x or the integral of x times fxx exist. Okay, so this comment exists because it is possible that we could have a random variable for which either the integral or the sum might not exist. We can use the idea of expected values to move on to calculating next important parameter for a random variable, which is the variance of the random variable. The variance captures the variation of the random variable from its expected value mu of x. The variance is typically denoted by v of x or sigma x squared. The x specifies the random variable. In the case when x is discrete, the variance is calculated as the expected value of x minus mu x squared, which is going to be the sum over all values of the random variable of x minus mu x squared times the PMF of x. On the other hand, if x was continuous, the variance again has the same formula. However, uh, it's going to be now the integral from minus infinity to plus infinity of x minus mu x squared times the PDF of x dx. The standard deviation of the random variable is going to be defined as the square root of the variance. We will next talk about some properties of the expected value, the variance, and the standard deviation. Suppose h of x is a linear function ax plus b, where a and b are real numbers. Then we can talk about the expected value of hx. This is going to be the expected value of ax plus b. And if we work out the formula, we notice that it's going to be a times expected value of x plus b, which gives us a nice formula for the mean of the random variable ax plus b, which says that if we scale the random variable by the factor a and translate it by the number b, the expected value is also going to be scaled by the factor a and translated by the number b. Working a similar calculation for variance of hx, we notice that the variance is going to be changed by a factor of a squared, and the standard deviation is going to be changed by a factor of absolute value of a. There is a nice shortcut formula for the variance of x. We can work out variance of x as the expected value of x minus mu x squared, and using the fact that the expected value is a linear operator, notice that we can simplify this equation to get variance of x to equal the expected value of x squared minus the expected value of x the whole squared. We finish this video with an example. Consider the experiment where we toss a fair coin 4 times. Let x be the random variable that counts the number of heads in 4 tosses. Then the probability distribution table for x is calculated as follows. The random variable takes values 0, 1, 2, 3, and 4. And we can then calculate the expected value of this random variable using the formulas presented earlier. Notice that the sum is taken over the values of the random variable, and the calculation proceeds as follows to arrive at the expected value 2. This says that if we toss a fair coin 4 times repeatedly, on average we would expect 2 heads in 4 tosses. To calculate the variance, we use the formula that the variance is equal to the sum over the values of the random variable of x minus mu x squared times pxx. Plugging in all the numbers, we notice that we arrive at the variance to be 1. We note that we can use the formula for the variance as expected value of x squared minus the expected value of x the whole squared. We calculate the expected value of x squared to be 5. And since we have already calculated the expected value of x, the square of expected value of x is 4. And we plug both of these into a formula and note that the variance of x is indeed going to be 5 minus 4, which is 1. This is the same as what we have calculated from the definition of variance. We will be talking about expected values and variances a lot in future videos, but this is all for now. Take care of yourselves, and I will see you around.